Welcome back to 5-Minute Chemistry. Today we are going to be talking about valence electrons and the Lewis symbols, which is the standard way to draw the valence electrons. If we consider the elements in the periodic table and what kind of ions they form, and for this exercise let's just ignore all the transition metals and let's just focus on groups 1 to 2 and groups 13 to 18. So groups are the columns in the periodic table, and we are going to take a look at the leftmost 2 columns and the rightmost 6 columns here. And we are going to assess what are the naturally occurring ions for the elements in these periods. So for the first group, for lithium, sodium, potassium and rubidium, the ions they form in ionic compounds is charge 1+, like sodium chloride or potassium oxide, etc. In group 2, we have magnesium, calcium, strontium, here which form ions with charge 2+ in ionic compounds. And in group 13 we have aluminium, which will form ionic compounds with the charge 3+. Let's skip group 14 and go straight to group 15, where we find nitrogen, which will form the 3- nitride ion in ionic compounds. It is not the most abundant ion ever, but it exists. And if we go to group 16, oxygen and sulfur will have ions which will have charge of -2. And in group 17, and for hydrogen, interestingly, so group 17, the halogens, and from group 1 hydrogen, they will have ions with the charge -1. So if you consider sodium bromide or magnesium chloride, all have these elements with ions at -1 charge. This is definitely a periodic character of the element. So first we can observe that while lithium has 3 electrons, it only loses 1 generally. So we talked about how you can remove technically all the electrons from an atom, but lithium will only lose 1 electron under general circumstances to form the lithium 1+ ion. Similarly, magnesium has 12 electrons but only loses 2, so we can establish that not all the electrons will take part in chemistry. So we can divide the electrons into valence electrons, which are participating in chemistry, versus core electrons, which are considered to be bound to the nucleus much stronger, so they do not participate in any chemical change. So electrons are organized in shells, and the outermost shell, which is the less strongly bound to the nucleus, will be the valence shell, which contains the valence electrons. And this was first described by G.N. Lewis in 1916 in his paper in the Journal of American Chemical Society, where he proposed this electron shell model based on the cube, because what we can find here is that, for example, lithium and sodium, they both seem to have a single valence electron, and the distance between these two elements in terms of their atomic number is 8. So if we go from lithium to the previous element from sodium, which is neon, so if we go from lithium to neon, we are filling up 1 valence shell, and when we go to sodium, we open a new valence shell. So this is why lithium and sodium has the same number of valence electrons. And based on that, a fully filled valence shell, which we have in case of the neon, will have 8 electrons. And Lewis's model said that neon and argon, so the noble gases, the valence shells are fully filled with electrons, which will be the most stable case, and all the other elements will form ions to reach this 8 electron structure, which he called the octet rule. So fluorine or chlorine only has 7 valence electrons, so they need to gain 1 more electron to achieve the octet state. So that's why they will form negatively charged ions with charge -1. And for example, magnesium, because it has 2 valence electrons, it cannot gain 6 electrons to fill up this valence shell, but he can lose the 2 electrons to have a full electron shell, which was the last shell under its valence shell. He used this cube model because a cube has 8 vertices, but drawing cubes is very difficult, so the Lewis symbols will symbolize the electrons using dots. And so for hydrogen, it has 1 electron, and this single electron is its valence electron, so we can draw a dot next to its symbol, and we get the Lewis symbol. For helium, which is a kind of strange one out here because it only has 2 electrons, but based on the behavior of lithium and based on helium being a noble gas, we can assume that the first shell is actually full with 2 electrons. So for helium, we draw the Lewis symbol with these 2 electrons next to each other in a pair to symbolize that this is a fully filled shell. And then for lithium, potassium, sodium, rubidium, we can get the Lewis symbol with a single electron. For group 2, we can have 2 electrons, so 2 dots. But unlike helium, these 2 electrons are not giving us a filled shell. So these 2 dots are drawn on the opposite side of the symbol of the element. If we go to group 13, here we will have 3 valence electrons, and we will put these 3 electrons all one by one. So if we jump to group 18 for the noble gases, except for helium, of course, we will have the fully filled shells with the octet structure with the 8 electrons, and to show that, we will draw the 8 electrons in 4 pairs. And if we go to group 17, which will have the elements where the atom has 7 valence electrons, so out of these 7, 6 will be in 3 pairs and 1 will be alone. So from this we can easily see that this valence shell wants to gain 1 more electron to have the full 8 electron structure. In group 16, similarly, we will symbolize that it needs 2 more electrons by having 2 electrons separately and 4 electrons in 2 pairs. In group 15, we will have 2 electrons in 1 pair, and the remaining 3 electrons will all be drawn separately. And for group 14, we will draw 4 lonely electrons at the 4 sides of the symbols. And if we are trying to draw Lewis symbols for ions, for example, magnesium loses 2 electrons. In the magnesium 2+ ions, we just don't draw any electrons because the outermost shell got emptied, and we can just assume, of course, that the previous shell is now fully filled. So for magnesium 2+, you don't have to draw any electrons. But when oxygen gains 2 electrons to get the oxide ion, which has 2- charge, you can draw all the 8 electrons and show that now we have filled up the valence shell. And lastly, if hydrogen gains an electron and becomes a hydride ion, let's not forget that for hydrogen and helium, the first period of the periodic table, actually the fully filled electron shell only has 2 electrons. So here we can draw for the hydride ion these 2 electrons next to each other. Okay, this is it for today, and I will see you tomorrow.